So in this video, I'm going to walk you through where to find what you need to do Lab 1. In Lab 1, I do have a few videos that I've recorded since I won't be there to help walk you through it. To get to this, go to Materials, Content, Labs, and then Lab 1. Every week in Lab, you'll have a PDF document that has instructions, so that's going to be a step-by-step set of what to do in the lab. In this one, it looks sort of like this. Well, it looks exactly like this. And there'll also be a Word document that has just the questions you need to answer. So these questions are also in that PDF description, but the only things you need to answer are the questions in this template. You'll download that, fill it out in Word, and then upload it to the link where it says Turn in Lab 1 here. Okay, so let's talk about Lab 1. The idea is to get you a little bit familiar with the kinds of energy units and power units that we use, using an example of something you do all the time, carrying a backpack up the stairs. So you'll need to know the weight of your backpack. My backpack's about 10 pounds. This was not a precise measurement. I know a gallon of milk is about 8 pounds. My backpack felt a little heavier, so I called it 10 pounds. This does not need to be precise, just ballpark estimate. To calculate the energy in the unit joules, which is what we'd like to do for this lab, we're going to have to convert that weight from pounds into a metric unit called newtons. And to do that, you just multiply by 4. The conversion factor is not quite exactly 4, but it's close enough for what we're doing in here. So in my case, so in my case, I get 40 newtons, because 4 times 10 is 40. To calculate the amount of work that I do in carrying that backpack up the stairs, I multiply the weight and distance, or the force I'm exerting, times the distance I go. So I've got 40 newtons, and it's about 7.1 meters to go up the stairs. If I multiply those out, I get about 280 joules. It's a little bit more than 280, but it's fine to round. We're going for ballpark here. So next, I find it helpful to think about this in food calories at first, and I'll show you the magical way that I do this kind of conversion. I go to my good friend Google, and I'll type in 280J for joules in calories, hit enter, and Google tells me the answer. So it's about 0.07 food calories. It says kilocalories down there because a food calorie is 1,000 calories. Now it turns out to walk up the stairs, to carry my backpack up the stairs, I've got to consume 4 times that amount of energy, that 280 joules, because my muscles only, or of the food I eat, only about 25% goes into things my muscles do. The rest of it goes into keeping your body warm. And so if I want to know the chemical energy, what did I need to input to be able to do 280 joules of work, I'll multiply the 280 joules by 4. Again, this is just to take into account the inefficiency of your muscles. And so if I multiply 280 joules by 4, I get 1120, I think? Yeah, 1120 joules. And next up, we're going to convert this amount of energy into kilowatt hours, which is the energy, or the unit that the book will often use for energy. And the conversion factors are up here. So 1 joule is a tiny amount of kilowatt hours. Is what that first conversion is saying. And the second one says the same thing, but in a different way, that 1 kilowatt hour is 3.6 million joules, or 3,607,000, or 3,600,000 joules. I like to stop and think about, when I do this conversion, is the work in kilowatt hours going to be a lot bigger, about the same, a lot smaller than the work in joules? And since 1 joule is a tiny fraction of a kilowatt hour, the work that we get in kilowatt hours should turn out to be pretty small. So to do this conversion, I could do it with my calculator, but I'm going to go to my good friend Google again and type in 1120 joules in kilowatt hours, and I get roughly, what is that, 0.0003. So, like I expected, it's a pretty small amount of kilowatt hours. So next up, we're going to calculate power, and we're going to do that in a couple of different ways. Oh, right, I just noticed that I should have had 1220 joules up there, not 280 joules. So power is energy divided by time. I estimated it took me 180 seconds to walk up the stairs. I guess I was feeling kind of tired when I did this. And to get power, you take the amount of energy that you used divided by time, and divided by time. In this concept of power is capturing the idea that it's harder to run up the stairs than it is to walk up the stairs, because when you run up the stairs, even though it's the same energy, you're using that energy in less time. So in this case, to get the power, I take my 1120 joules and divide by 180 seconds, and I get, I think it's, well, let me double check, 6.2 joules per second. And a joule per second is a watt, so it's 6.2 watts. So next up, we're supposed to calculate the power in kilowatt hours per day, because that's the unit that the book uses. I've got step-by-step how you could do that as a bunch of individual pieces. Convert the energy to kilowatt hours, convert 180 seconds to days, divide the two. I don't recommend doing it this way, because there's lots of opportunities to make a mistake. Instead, just divide by 41. So if you have the power in watts, 6.2 watts in this case, divide it by 41, and that'll get you the power in kilowatt hours per day. And if I do that here, I get 0.15 kilowatt hours per day, which is the same thing I got when I did it the long way, but this is quite a bit less painful. And that's a run through of all of the calculations we'll need to do in this lab.